In the previous lecture, we saw how to handle the case of complex poles. So we can use this standard form for the quadratic case, and how we approach plotting it then is to first work out what Q is, and if Q is greater than a half, then we have complex poles, and we can plot the magnitude and phase responses as described in the previous lecture. However, in the case where Q is less than a half, then we have real poles, and what we would still like to do is to factor the denominator into two real poles like this, and then plot it using the rules for real poles. So we're going to consider today, or in this lecture, the details and mechanics of how to factor this and plot as two real poles. So here's an example back to our RLC network where this was the transfer function. This was the example in the previous lecture. Let's factor the two roots, and what we find is omega 1 and omega 2 are given by this expression using the quadratic formula with the radical and the plus and minus sign. Now, I think that this expression for the two corner frequencies is not very illuminating. It's pretty hard to just look at this expression and tell how the corner frequencies depend on the different element values. If you change, say, L, what does that do to the two corner frequencies? It's actually interesting to know that, in fact, when the Q factor is much less than a half, that the two corner frequencies can be approximated like this, where omega 1 is R over L and omega 2 is 1 over RC. So, for example, omega 1 doesn't even depend on C, and omega 2 doesn't depend on L. But you'd never know that from looking at this formula. So the simpler and approximate equations are actually more useful. They gain more insight as to how the corner frequencies depend on the element values, and they're easy to solve. You can see how to change an element value to if you want to adjust the value of the frequency, which you would never get out of this formula. Okay, we're going to define omega 1 as the low frequency pole, which is found by taking the minus sign, and omega 2 is the high frequency pole found by taking the plus sign. And what we're going to do is derive a simple approximation to get expressions like this without having to use the ugly quadratic formula. So the way I'm going to state it is, if we start with this standard function, the first thing we will do is find Q. And in the case where Q is less than a half, then we know we have real poles and we will factor them. Whereas if Q is greater than a half, then we will use the quadratic form as in the previous lecture. So when Q is less than a half, we factor the poles, and the quadratic formula tells us that these are the expressions then for the two poles. And you can note that when Q is less than a half, then 1 minus 4Q squared is positive, so we get a real result for the roots. Okay, let's look at whether we can approximate these functions in a much simpler way. So I'm going to look first at omega 2, the high frequency pole. So here was the expression we had for omega 2, and it has a term out in front that is omega naught over Q, and then it has this more complicated term that has the radical in it, and I'm going to call this more complicated term f of Q. If we look at what f of Q does as a function of Q, first of all, when Q is small, so much less than a half, then 4Q squared is much less than 1, and what we could do to approximate f of Q is just throw out the 4Q squared term, and we get 1 plus root 1 over 2, which is just 1. And so for low Q, f of Q actually goes to 1, which is what's plotted here. As Q approaches a half, then this function approaches just 1 over 2, and the discriminant goes to 0. So the f of Q goes to a half at Q of a half. And in fact, it changes very quickly for Q in the vicinity of a half. If you, in fact, look at the function for Q less than 0.3, f of Q is between 0.9 and 1. So if we just called f of Q equal to 1, we'd be within 10% of the right answer for Q less than 0.3. And it's only this last little part here for Q between 0.3 and 0.5, where f of q changes much at all. So the low q approximation says, then, for omega 2, let's just take the f of q function and call it equal to 1, and approximate omega 2 as being omega naught over q, this part of the expression. Okay, how about the omega 1 term? Here's omega 1, it has the minus sign, so if you try the same thing, and say, okay, let's let 4q squared be much less than 1 and ignore it, what you get then is 1 minus 1 over 2, or 0. So then we're approximating omega 1 as 0, which is not a very useful approximation. So we need to do a little more work. And here's a trick, a way to do it. What we do is you can think of this as rationalizing the numerator. We're going to multiply by 1 plus the radical in the numerator and the denominator. And if you multiply this term by this term, it removes the radical from the numerator. And you can do the algebra. I'll let you do that on your own. And what you can show then is that omega 1 is given by q omega naught over f of q, where f of q is the same function we defined on the last slide, which we've already plotted. So for omega 1 then, we get q times omega naught divided by the f of q, and again f of q is close to 1, particularly when q is less than 0.3. So the low q approximation then approximates the low frequency pole as omega 1 is q omega naught. So then here's a summary. For the two-pole case, when we have low q, the two poles split into a low frequency pole omega 1 and a high frequency pole omega 2, and they're in fact spaced evenly about this resonant frequency f naught. It's no longer resonant, but so f1 is f naught times q, where q is a small number, and f2 is f naught divided by q. If we increase q, the two poles move together towards f naught, and then in fact when q is greater than a half, they turn into a resonant response with a resonance at f naught. So what we do then is we calculate q. If we find q is less than a half, then we can use the low q approximation and quickly get the real poles from these expressions. Back to our RLC example. Here was our original transfer function, and here are the expressions that we had for f naught and q. So f1, we said, would be q times f naught. So q is r root c over L, and f naught is 1 over 2 pi root LC. So the root c's cancel, and what we get is r over 2 pi L. It's a nice simple expression. For f2, we said that was f naught divided by q, with f naught again is 1 over 2 pi root LC. And 1 over q is 1 over r times root L over c. So let's see, the root L's in this case cancel, and we get 1 over 2 pi r times c. So again, nice simple expression. So the low Q approximation gives us a nice way to keep control of the algebra and get simpler expressions that are easy to use in design.